Hear me okay? All right, good. So yes, thanks very much for the organizers for inviting me to this talk. It's a great pleasure. This is going to be a joint work with Ian Sullivan, Jake Khovanov, and John. All of them are present, I think. So if you have any questions, maybe I think some of us should be able to answer you. Okay, so I'm going to, this is a conference about new structures, and I'm going to present some new structures. So this is not going to be about the original Khovanov skein lasagna modules, but ones with one-dimensional inputs. So today, my talk is going to consist of 3 parts. Part 1, I will explain what do I mean by skein lasagna modules with one-dimensional inputs. And the second part, I'm going to outline, maybe introduce some new ingredients we have in order to prove what we need. And in the last part, I will give a sketch of the construction for the input TQFT. Well, part 1 about the definition, I would like to start with the original skein lasagna module. So recall that the Khovanov skein lasagna module, sorry about that. Khovanov skein lasagna module, and I will call with 0-dimensional inputs. This is an invariant introduced by Morrison, Walker, and Wojcik. It's assigned to every 4-manifold, every pair XL, where X is a smooth-oriented 4-manifold, and L is a link in the boundary of X. This is an invariant of this pair denoted by this script as 02 XL. This is a vector space generated by Lasagna fillings. Those are pictorially. I have my 4-manifold X, probably with some boundary, and maybe on my boundary I have a link. Okay, maybe I want to use blue for the skein. So this is my L, and the lasagna filling is some surface in the interior. An embedded surface in this 4-manifold whose boundary is L, but the surface is not directly inside the manifold itself, but it's rather inside the manifold with finitely many foreballs deleted. Those foreballs B1, B2, B3, for example. And I have a surface in the complement of those foreballs, but it may have some boundaries on those input foreballs. And may have some closed components. So by dimension count, the boundary of those I call skeins will have link boundaries on those input balls. And on each of those links, the lasagna filling consists of the data of some declaration, V1, V2, V3, where Vi is a label in the Khovanov homology of the input link Li. Li is the intersection between my skein and the ith foreball. So it's the boundary of the surface on that input ball component. All these modules know some skein relations, where the skein relation is generated by, there are more or less 3 kinds of relations. The first one is, as usual, we model out by isotopy of this picture. So I can isotope my input balls around, and I can also isotope my surface around. that should, okay, sorry, this is a vector space generated by those Nassanian fieldings over coefficient field Q. If I isotope such a Nassanian fielding, this should not change the class it represents in the skein Nassanian module. The second relation is linearity. So those labels V1, V2, V3 should really be think of as V1 tensor, V2 tensor, V3. And if I have a different Nassanian fielding with the same underlying skein, then I can add up those labels in a multilinear way. The last relation is the most interesting one. I call it the enclosement relation, and I'll draw a local picture for that. So suppose that somewhere in your four manifold, you can see a part of your skein. Maybe there are some four balls, and there are some part of your surface attaching to it, like this. And we have labels on the boundaries of those input balls. And suppose we can enclose a certain local part of this picture by a slightly larger ball, like this. Then we can delete the inside of this larger four ball and replace this local picture by this new skein, where I only remember the outside of my skein, and this is a new input ball. And I also need to update the label V1, V2 to some new label on the new boundary. But this is supplied by the data, by the functoriality data of the Khovanov homology. More or less, you need to choose a path connecting up the inside balls, and then the rest of the complement is S1 times I, and then you know how to evaluate. Maybe I should also, as part of the notation, those BIs, those are four balls. I already said them vocally, but I want to emphasize that the explicit parameterizations between those BIs and B4 are not a part of the data. And but in the usual Khovanov skein Nassanian module construction, this is a really minor issue, and really for the construction to work, you need to say something else about the parameterizations, but let's not worry about that right now. Some remarks about this construction. Well, the first remark, why we delete B4. Well, to me, maybe there are two parts of the reason. The first thing, it would be more natural to directly study embedded surfaces inside my four manifold without deleting all those balls. But Khovanov, and okay, if we do it that way, then it's natural to impose some kind of local skein relation by saying that if I have two different skeins differing only in a local four ball, and inside those local four balls, I get the same. I evaluate it using the Khovanov functor to get the same vector in the Khovanov homology of the boundary link. Then I should declare those two skeins to be equivalent. That is good, but the problem is that Khovanov homology of a link is not generated by nice surfaces. In B4. So if you were in this morning's talk at last talk by Matt Hogenkamp in 3 dimensions in the Barnard-Tan skein Nassanian module, there's really no this issue. Every link in the boundary of a three ball is an unlink, and its Khovanov homology is generated by nice surfaces. but this is not true for Khovanov homology in our dimension, so we have to, it's best if we manually introduce those new declarations by deleting foreballs.
When you say slice certain, you don't mean from typing a zero.
Oh yeah, it's just any, yes, sorry, maybe that's not a good name by surfaces. Yes. Okay, maybe that's okay. Yes. Okay, thanks. Embedded surfaces in P4. Okay, the second reason this is reasonable is because, well, deleting foreballs does not change, does not destroy the topology of a four manifold. Because you can fill them in. Okay, and maybe a second remark, from the construction, you recover whatever input TQFT, in this case Khovanov homology, you use, because pretty much straightforward from the definition, you can prove that there is a tautological isomorphism between the skein lasagna module of a four-ball real boundary link and the input homology theory on your link. This is a statement on the object level, but you can also recover the functoriality by gluing a corner to in the Lasagnian world. And third remark is because the construction, the definition is very topological, one can quite easily obtain certain handle attachment formulas. Namely, one can study how does the skein lasagna module change under attaching a new handle to my four manifold, express the new skein lasagna module in terms of the old one, maybe with some extra data. So this was done, I guess, so there was work by Mănănescu, Netanet, and also Mănănescu, Walker, and Rodrick. And using those, well, in particular, the two-handle attachment formula, me and my collaborator Vonis showed that the Khovanov skein lasagna module can detect exotic smooth structures. However, those handle attachment formula, well, I guess in particular, the one handle attachment formula, maybe those are different items. When my four manifold has one handle, if you want to directly apply the theoretical handle attachment formula you get in this second paper, this formula is just too complicated. And it doesn't seem to go anywhere by directly using that. So today, instead of sticking with the original definition of skein lasagna module, I'm going to modify the construction a little bit, hopefully to resolve at least this issue of one handle attachments. And maybe I'll talk about the definition and pointing you to some of these remarks as I go. So I'll just change the word here. Okay, definition. The Khovanov skein lasagna module with one-dimensional inputs of a pair XL is maybe I'll just put a bar here to distinguish it with the original definition. This is generated by Nassanian fillings like this, modular relations, but by Nassanian filling, those input balls, I don't want them to be balls anyway. The balls are some zero-dimensional objects. In other words, a ball is a turbulent neighborhood of a zero-dimensional CW complex embedded in my four manifold. But I want to replace that by a turbulent neighborhood of some one-dimensional objects, namely an embedded graph. So the corresponding neighborhood is going to be diffeomorphic to a boundary sum of S1 times B3s. Maybe I'll keep that picture there. It's just the schematics. And everything else on this board works fine, except I have to tell you what this label means, because now my input links are living in the boundary of such four manifolds, which are connect sums of S1 times S2s. So I don't need to tell you what do I mean by that, by Khovanov homology there. And as for relations, isotopy is fine. Linearity in the labels is fine as soon as I tell you what are the input homology theory. For the enclosement relation, we still take this same picture, but you should not be misled by the simplicity of this picture. So in reality, what can happen? Maybe I'll just draw a different picture to illustrate what complication can arise. So let's draw a single S1 times B3. This is, maybe let me put this smaller. So this shaded region is my S1. It's a copy of one S1 times B3 embedded somewhere in my manifold. And inside of it, maybe I have a curve winding around the S1 direction twice, like this. This is a curve in the embedded curve in the interior. And I can thicken this curve a little bit and delete the neighborhood of it. Not sure how to draw it properly, so I just thicken like that. So this now the neighborhood of this curve is another copy of S1 times B3. And now if I have a link in the boundary of this inner S1 times B3, what color can I use? Maybe red. And a link on the outer boundary. And a link cobordism going in between like this. I need to assign you a map from the homology on this inside link to the homology of the outside link. So we need a very good functoriality property for our input link homology in connect sums of S1 times S2s. And we need this assignment to be in a functorial way when we compose. Okay, one immediate remark is this is going to be reasonable because deleting some one-dimensional stuff in a four manifold does not destroy the topology of the four manifold. And a second remark is that then if we make this definition, as long as we understand the input TQFT very well, then one handles will no longer be a problem because then, because once the construction is in place, if I have some one-dimensional stuff, meaning boundary sums of S1 times B3s as my four manifold and an arbitrary link on the boundary, then this one-dimensional input Khovanov skein Lasagna module is just going to recover whatever input homology we are using. You do get somewhat different two-handle attachment formula, but maybe that's for another talk. Okay. All right. So maybe let me write down the theorem. Our main theorem is basically saying this can be done. And it can be done for the so-called Rosansky-Vonis invariant. The Rosansky and Vonis define a Khovanov homology for links in convex sums of S1 times S2s. This supplies the input homology theory. Okay. So there was already a well-defined link homology theory for links in such kind of manifolds, but what was not known was the functoriality in particular, or this kind of maps. I should emphasize that it's not even known that this homology theory is functorial in just S1 times S2 times an interval, because there are some movie moves, etc., that people are tired of checking them. But we do much more than just that. We have all these various kind of complicated cobordisms. And maybe I should emphasize at this moment that we are doing this in a very unconventional way. But I'll leave some suspense at this moment and talk about something else. Okay, so let's get into the second part of the talk, which is some new ingredients. Of the proof. Maybe I forgot to label. This is part 2. So I want to, so maybe I should say at this point that it might not be immediately clear what I'm going to say has anything to do with what I was describing over there. But let's talk about some of the ingredients. Ingredient 1, so we have a theorem, and that D standard denote a four manifold, a convex sum I from 1 to k, boundary sums of mi copies of D2 times S2, where k is greater than 0 and I greater or equal than 0. This is a very particular four manifold. Doesn't seem to have anything to do with the picture over there. The theorem is that there is a short exact sequence of topological groups. One goes to diffeomorphism, real boundary, local. I will expand the notation in a bit. Of this four manifold maps to diffeomorphism group real boundary of E standard. So this is the diffeomorphism group of this particular four manifold real boundary. And this maps to some abelian group of rank m times m minus 1 divided by 2 and some z mod 2 factors. Z2 k minus 1 to 0, where m is a sum of mi. And where this diff local, diff real boundary local, this is defined to be the subgroup of diffeomorphisms that can be supported, that can be isotoped to be supported in a local four-ball. So that phi is isotopic real boundary to some psi. Psi is supported in local B4. Okay. And just some more information about this theorem. So where do those z factors comes from? Those are represented by diffeomorphism that people call barbell diffeomorphisms. Those are studied by Bartley and Gabay. And those Z-mod 2 factors comes from Dan twists along embedded 3 spheres. And it will be it will become an important ingredient of our theorem over there. Maybe let me also mention a corollary of the theorem, which is that the smooth and the topological mapping class groups of this manifold D standard fit into a short exact sequence. One maps to pi 0 of diff real boundary B4 maps to pi 0 of diff real boundary. This is the smooth mapping class group of my 4 manifold. This maps to the topological mapping class group. Of the 4 manifold maps to 1. And the proof is, so the topological mapping class group for simply connected 4 manifolds real boundary are studied by Powell and Orson. And we just check that if you mod out by local diffeomorphisms, you get the same set of generators.
The barbells and the big twists are non-trivial, just the same in the topological category of the manifold.
Yes. So yeah, maybe one word on proving this theorem. The way to prove this is to show if you have a diffeomorphism here that is maps to this 0 over there, this map is going to be detecting some change in relative second homology as well as relative spin structures. But if you can show a diffeomorphism acts trivially on those, then you can first fix some arcs with framings to reduce this manifold with just boundary sums of D2 times S2s, and then you use Gabay's Nightbulb theorem to four-dimensional Nightbulb theorem to show you can also fix some co-core disks to reduce it to a 4-ball. And one can probably also do this by some embedding calculus argument, but maybe I don't want to get too much into it. Okay. This will be important somehow. And I will try to explain that, but after some other ingredients. Sorry? Here? I think so. Yeah, I think so. Second ingredient I want to talk about has something to do about this so-called Gauge twist construction. So maybe I'll first introduce what do I mean by a Gauge twist. So let X be a smooth-oriented 4-manifold, and that S in the interior of X be an embedded unoriented 2-sphere. Then, okay, with trivial normal bundle. This trivial normal bundle condition just means if you take a turbulent neighborhood of my embedded two-sphere, this is going to be diffeomorphic to just D2 times S2. You choose an orientation to get the S2 factor, but you don't need to make any choice for the D2 factor. The Gauss twist of X on the two-sphere S is a new four manifold, X sub S, defined by I delete this turbulent neighborhood of my two-sphere S, and I regrue it in by a twist along the common boundary, which is S1 times S2. So via this chosen diffeomorphism identifying the turbulent neighborhood with D2 times S2, boundary is canonically identified with S1 times S2, and tau is a den twist along the S2 factor, or equivalently is the only long spin mapping class that is preserving the orientation. And some properties of this Gauss twist enjoys includes the following. So if my two-sphere S bounds a three-ball B inside my four manifold, this is just to say this two-knot S is unknotted. But I actually want to specify this three-ball B. Then the Gauss twist is trivial, meaning it's canonically diffeomorphic to the original four manifold you start with, where canonical means dependence on the three-ball, but nothing else up to isotopy. The second property is if you do a Gauss twist twice, you obtain the original manifold back. So if you do Gauss twist once, you still see S in the core of this neighborhood you regroup back in, and I can twist it again. This is canonically diffeomorphic to what I start with. And the third property is that if I have two knots with trivial normal bundle, S1, S2, inside X, and gamma is a path connecting S1 to S2. Is an arc, let's say a framed arc, connecting S1 to S2. Then an operation we can do is to take the connect sum of S1 times and S2 along this framed arc. In that way, we get a new unoriented two-sphere with trivial normal bundle. And the conclusion is that if we perform the Gauss twist along this connect sum S1 times S2, then this is going to be canonically diffeomorphic with dependence on this framed arc to the iterated Gauss twist I perform first on S1 and then on S2. Okay, so the second ingredient of our work is a Gauss twist construction in skein lasagna modules. So theorem, so that X and L and S be as before. So XL is a pair of four manifold and a link on its boundary. S is a two-sphere with a trivial normal bundle. Then there is a canonical isomorphism we denote by tau dependence on x, L, and S from the skein lasagna module of XL to the skein lasagna module of the Gauss twist on X, real L. So in particular, skein lasagna module is insensitive to Gauss twist construction. And moreover, well, in the situations 1 through 3 as above, those nice relations about Gauss twist are preserved by our construction. So number 1, if S bonds a 3-ball inside my 4-manifold, then the Gauss twist lasagna Gauss twist map is equal to the identity map. Really, by this I mean, so I have a Gauss twist map on skein lasagna, tau. And I have an identity map, but those two maps really have different targets. I mean that this diagram commutes under the canonical identification between XS and X given by this diffeomorphism. This diagram commute, this is what I mean by this is equal to identity. Second thing is if I first perform a Gauss twist on a two-sphere and then perform the same Gauss twist again on this Gauss twist twisted 4-manifold, then I get the identity map. And the third thing is that if I perform lasagna Gauss twist on a connect sum of two knots, then this is equal to the iterated Gauss twists. Okay, this is the second ingredient. Okay, question? Yes.
Does that little gamma under the equal sign mean that there's that it does actually, it takes into account those two paths?
So those two maps have different targets, but the targets are canonically identified by with some dependence on the path.
So, I mean, logically, at the moment, we don't know that the Khovanov Rosansky topology is the correct sum of this one. We don't know it yet. How
We don't know anything about it yet.
yeah, but I mean, these are tools improving.
Yes, this has nothing to do with the Rosansky-Ronis homology yet. Right. Okay. The third ingredient, maybe I'll be brief. This is about functoriality of the Khovanov homology. So some history. So for the original Khovanov homology for links in S3, it was proven by Jacobson up to sign, and later many people, and finally Christian Blanchet showed that KHR2 is functorial for links in R3 and link cobordisms. But in order to build the original version of skein lasagna module, one had to improve this R3 to S3. So there was this was done in the work of Morrison. Maybe I'll just abbreviate as MW. This is the definition of skein lasagna paper. KHR2 is functorial for links and link cobordisms in S3. On the other hand, one can also define Khovanov homology for webs and foams, and it was checked by Khovanov also in 22 that Khovanov homology is functorial for webs, for GL2 webs, and GL2 foams between them in R3. So one can fill this in. And let's state this as a theorem that KHR2 extends to a functor from the category of GL2 webs in S3 and generically immersed GL2 forms in I times S3 with no double points between thin and thin edges. If you don't know that means, ignore this for a moment. Double points between thin and thin faces to the category, say, of vector spaces. So this, this not only extends the functoriality of GL2 webs and GL2 forms from R3 to S3, but also we are now in those immersed forms with possibly transverse double points between thin and thick faces and thick faces. This is only going to be relevant for some sign fix reason, so hopefully it will not come up again. So that's it for the second part of the talk. Any questions? Yes?
Is it actually important that you keep like the interior thick faces around, or can you just like erase them and put a tag on?
If you erase the thick faces, you are going to get some sign ambiguity. So I guess this theorem is really saying we can fix the sign.
Right, but I guess what I'm asking is, do you really need the whole interior fixed, or is it enough for this one?
Yeah, you are right. Well, let's see. I think you need to remember, okay. So this is certainly going to be invariant on the Whitney moves and finger moves and some generalizations of that. But maybe I'll get back to your question a bit later. All right. Okay, so how are we supplying the data for those induced maps on Rozansky-Vonis homology? So part 3, I sketch proof, sketch construction. Really, I surprised one other very important ingredient, but it was done in an earlier paper by Ian Sullivan and Melissa Zhang. 24. That says, I'm rephrasing this a little bit, but that B standard, be the sum manifold appeared as before, a connect sum of boundary sums of D2 times S2, and that L be a link in its boundary, then the skein lasagna module of the pair D standard real boundary link L is recovering the Rosansky-Vonis, not quite, and putting something here. Some homology of my link L tensor some so-called Qiuyu factor, just the skein lasagna module of the manifold itself with empty boundary link condition. So they prove that there is not quite canonical, but if you fix a link diagram of the link L, then you get a canonical isomorphism between this skein lasagna module real boundary link L to this is kind of a dual of the real Rosansky-Vonis homology. So it's actually Rosansky-Vonis of the Miro, and then take dual, where this dual is taken as graded vector spaces. Not so important for the purpose of this talk. So we have, in other words, we have a Nassanian way to understand the Rosansky-Vonis homology because it appears purely in terms of the construction of Khovanov skein lasagna module. And I should emphasize this is quite remarkable because the construction of skein lasagna modules has, with zero-dimensional inputs has nothing to do with this Rosansky-Vonis homology. But somehow we can recover that from here. Okay. Maybe I want to say a little bit about this factor. So for D standard, the skein lasagna module is supported. One can really write down a formula of this, but I'm short in time, so I'm not going to do that. But I'll tell you this is supported in quantum degree less or equal than 0. And there is an H2 action. H2 of this manifold acts it actually acts on the whole skein lasagna module, but for our purpose, I will want to quotient out this skein lasagna module by everything that is below quantum grading 0. So this Q minus 0 is the submodule of lower quantum degrees. Maybe let me introduce a shorthand and denote this by D standard. I don't know, quotient less than 0. This is the notation for that. So there is an H2 action by, let's say, just introduce some notation as alpha mapping from this quotient of skein lasagna module to itself, one for every class in the second homology. This is a group action. Okay. Now magic comes. What are we doing? Well, let's consider. So we have a disjoint union of some standard manifolds. Those are each diffeomorphic via some unspecified diffeomorphisms to boundary sums of S1 times B3s. And inside of its boundary, I have a link. Let me just call it L0. It's going to split up into different components. This is a disconnected manifold. But this is so this is the inside of the thing. So remember this picture. We have some outside four manifold, we have some inside four manifold, and we also have a link cobordism going between like this. So this is the inside blue four manifold. This is the inside red link. There's an embedding to the outside. Let me also use a disjoint union, another disjoint union here, BJ1. This is the outside four manifold. And on its boundary, we have an outside link, L1. And in the complement of this embedding, we call it I have a link cobordism sigma going between L0 to L1. So this sigma is the surface. Outside link is L1. Inside link is L0. The whole four manifold is this BJ1, and the inside blue manifold is disjoint union of BI0. Okay, now turn this around, and by that I mean I choose an embedding from this outside manifold into S4. Let me call it iota. There are not much choices for embed some one-dimensional stuff into S4. You basically have to specify where does the core go, but there's no choice for that, and there are some ZMO2 framing choices involved, but that's all. And now we can turn the whole picture around. So what this becomes, well, we have S4 minus the outside. This embeds into S4 minus the inside. And on the boundary, I still have my links, maybe with reversed orientation, L1 and L0. And I also have a reverted cobordism sigma t going in between. But now the thing is that after we turn around, the complements of those four manifolds becomes diffeomorphic to do some connect sums of boundary sums of D2 times S2s. And let me denote this by D standard 1, and this by D standard 0. D standard 0 is some concrete manifold of that form, and we are fixing some parameterizations, phi1 and phi0. Okay, now now we get this new picture, and let's simplify the picture a little bit. We get a cobordism from L0 to, from L1 to L0, the backward direction. This lives on the boundary of D standard 1, this on D standard 0. There's an embedding between four manifolds. But now we can ask, what does this do on skein-Lasagna modules? And let's state theorem. Not sure how many more theorems I can state, but let me state the first one at least. So this diagram gives you a Green map on the level of skein-Lasagna modules. You just screw the complement of this embedding together with this surface. onto a corner of onto the boundary of this smaller manifold. But on the other hand, by Ian and Manisa, we know there is this isomorphism saying that this is more or less recovering the Rozansky-Wilnis homology. And similarly for the other side. But we actually want to project it to this Q equals to 0 quotient for some technical reason. Okay, and now, okay, this map is the Lasagna Green map. It's already defined. The theorem is that we can fill in this lower arrow by some map of the form KHR2 plus sigma t tensor as some group action, then okay, this is a node. So we have an embedding from D standard 1 to D standard 0. This embedding is going to induce a map on skein Lasagna module, which I denote by S of I transpose. I compose that with some group action S alpha. This is a map from the second factor to the second factor. This descends to the quotient. This gives the second factor, and I have another map in the second factor. The claim is that this diagram commutes for some maps KHR2 plus sigma transpose and some class alpha in H2. So basically, this is going to those KHR2 sigma transpose, after you dualize, will supply the maps on Rozansky-Wilnis homology. And the fact that this is a functorial assignment will follow from the fact that the Lasagna-Green map is manifestly functorial. But this is not yet enough because in the process here, we made some choices. In particular, I think we made some choices, phi 0, phi 1, to identify those complements of standard form manifolds to some really standard pieces of this standard form. And we also have chosen an embedding iota. So I think I started slightly late, so maybe I'll take 5 more minutes. I'll tell you how to remove the dependence on those choices and how that relates to the ingredients we have mentioned. Let me write down theorem B. It's not very precise as I stated, so I'm putting quotation marks, but I'm not going to explain. So theorem B is that if I have a parameterization change, then I have a diffeomorphism real boundary of a manifold I call D standard, and L is a link in the boundary of D standard, then this diffeomorphism is going to induce the map on the skein Lasagna module. This is induced by phi to itself. But I can also construct this diagram over there using this isomorphism to compare what happens on the level of Rozansky-Wilnis homology. Maybe I'll omit the middle step and go to the last row. this is the same term. Okay, the theorem is that, okay, I don't want to erase everything. This computes for a certain map of the form KHR2 plus phi tensor shift by class alpha. This computes for some KHR2 for some parameterization change map on Khovanov on Rosansky-Wilnis homology and some second homology class. And this gets rid of the issue of those parameterization changes. And the way we prove this theorem is by decomposing the diffeomorphism phi into a product of local diffeomorphisms, barbell diffeomorphisms, and den twists. So it will be more or less straightforward to see that if you have a local diffeomorphism, that's not going to change the skein lasagna module because 4-ball is too small to hit any surface. And one can also easily show that den twist is not going to change the skein lasagna module. But there are some work to do with the barbell map. And about this embedding, this has something to do. Oh, I'm erasing part of my theorem. About this embedding, this has something to do with the gauge twist operation. So the theorem is that if I have a diffeomorphism orientation preserving diffeomorphism of the boundary and S inside the interior of the 4-manifold is a boundary parallel to sphere. And suppose we can extend the diffeomorphism on the boundary to a diffeomorphism from D standard to D standard gauge twist on S extends phi, then we can form a similar diagram, skein lasagna module of D standard real boundary link phi of L perform the lasagna gauge twist D standard S, phi of L S to skein lasagna module of D standard gauge twist phi of L, but now I can use phi inverse to identify it with the gauge twist with D standard, but changing some boundary parameterizations, therefore sending phi of L to L. Then if we compare what happens on the Rosansky-Wilnis level, phi of L. Tensor is some factor. Here, tensor is some factor. This is going to compute for some map, for some parameterization change related to phi, tensor some parameter shifts. This computes for some maps of that form. And this is to get rid of the issue of choosing this embedding iota. Okay, sorry for going over. Okay.
Questions?
Yes.
Just trying to understand what magic happened when you took the complement. If I just started with S1 times B3,
Yes.
and with the sort of classical zero-dimensional input, it's sort of skein lasagna,
Mm-hmm.
like some link error on the boundary. If I've got a diffeomorphism real boundary of S1 times B3, is it obvious before that
Uh,
taking the complement trick, or
somehow miraculously, after taking complements, we are forgetting any parameterization issue on the original S1 times P3 overall. And yeah, I guess I didn't have enough time to properly explain the part of how we are really proving we are doing everything properly. Yeah, basically, you don't need to remember the parameterization on S1 times P3. Maybe that's a short answer.
so it's still not clear whether such a diffeomorphism would be the identity, and it no longer matters to you, this construction.
Oh, yeah, I think, yeah, I understand your question. Yeah, I think it will induce the identity map on the, well, so really the input homology theory only depends on the link in the boundary of S1 times P3. The interior doesn't matter. The interior only matters when you consider cobordism. So when you have this kind of picture, the parameterization in the complement of the blue in white matters, but the parameterization inside the blue does not matter.
Perhaps I'm misunderstanding something, but theorem A to me seems to be providing evidence for the functoriality of Kaczynski Lewis homology using the skein lasagna modules of S2 cross D2. But how does that help me define skein lasagna with one-dimensional inputs? Because as I understand it, this S4 is just some abstract S4. It might not a priori live in the interior of my four manifold that I started with.
Oh, yeah, so the whole point of turning this cobordism around is to define those maps which we need for the purpose of constructing one-dimensional input skein lasagna module. We only need to, so we have a theory for link homologies in convex sums of S1 times S2s. We also need the theory to this input to tell me what to do with a link cobordism between, as in this picture, or any other possible pictures that can arise. For example, if I have a 4-ball and I have a little S1 times S2 inside, and I have a link cobordism going like this, I need to assign map from here to there. And if I embed this B4 to something larger, I get another induced map, and this assignment is in a functorial way. But the point is, by this abstract skein lasagna module construction, what we really need is a theory that is functorial with respect to all those pictures. Once I give you those data, the definition of one-dimensional input skein lasagna module is complete. Sorry, can you repeat the question?
So you can forget the complication of the surface cobordism because you can now just consider a bunch of cylinders that run from the boundary of your four manifold to
So,
the body.
so I'm not forgetting the complication of this morphism. I'm just turn.
Push that into like this solidity.
Yeah, I'm embedding the whole picture inside S4, and I look at the complement of this picture.
I mean, in the lasagna module.
Oh, in the skein lasagna module.
Make your, I mean, the one complex that you consider, you can make it a bit bigger to fill all the topology of the surface, right?
Right, you mean in the one-dimensional input, the skein lasagna module? It's going, maybe I didn't quite understand the intended question. Sorry about that.
Yeah, so like let's say we do it 4 micro doesn't have the one handle. Do you expect like this version like coincide with the version of the
No, I don't think so. So when the 4 is simply connected, this new version is going to be a quotient of the original version. So presumably the computation could be simpler, but it also carries less information a priori.
Another question.